are some 1,248 major and medium irrigation schemes in the country. And during the past 4 decades, there have been a dramatic increase in the use of groundwater for irrigation. And as a result, India now has the world's largest gross irrigated area, especially addressed by agriculture. The irrigation development has been widely acknowledged to have helped our country not only to achieve food self-sufficiency, but also to be an exporter of agricultural produce in recent times. But with irrigation development, the tendency of monocropping and over-irrigating in canal command areas is also emerged, resulting into salinization and waterlogging of good arable land of our country. So drainage is one of the areas that has not been given an adequate and equal status as irrigation. Just we were discussing this with Bundela sir. So during the era of Green Revolution, drainage provision were generally deferred or postponed in many cases due to want of funds, and thus was left to be taken subsequently as a curative measure to address the waterlogging and salinity problems as and when encountered. So it was not essential part. But land drainage is very important, especially to remove excess soluble salts with the excess water from the soil profile, facing different situations like excessive rainfall or due to the leakage of canal lining, seepage from canals, also due to over-irrigation. So land drainage actually prevents the decrease in productivity of land due to the rising water tables and accumulation of salts in the root zone. So looking at the importance of surface, subsurface drainage systems in sustaining the agricultural productivity of our land, on behalf of the CAST project, we are offering this 1-week online training program addressing issues such as planning, layout, design, installation, cost estimation of agricultural drainage systems, its national guidelines that are developed by a renowned institute, ICR institute, like the Central Soil Salinity Research Institute of Canal, and along with keeping focus on related topics such as physico-chemical nature of salt-affected soils, their reclamation and maintenance, cultivation of salt-tolerant crops, and role of geospatial technologies. And we have also added some case studies in this 1-week training program. So we have knowledgeable leading experts with us for conducting this program. Dr. Bundela is one of them, Dr. Kaledhonkar from CSRI Karnal, Dr. Karegaudkar from Raichur, Dr. Rathod, Dr. Katmale from ARS Digras, Dr. Kamble from Agriculture College Dhule, Dr. K.D. Shinde from Astral Polytech, Mr. Hegenna from one of the community drainage project of Shirol, Dr. Gorantiwar, who is head of agricultural engineering and principal investigator of CAST project at MPKV Rahuri. So this is a team of experts, and I'm really requesting all the participants to take benefit of their expertise in respect to this topic. I wish you all the best for attending this training program. Today, I invite our first expert, Dr. Devendra Singh Bundela, who is a principal scientist and head of Division of Irrigation and Drainage Engineering at ICR Central Soil Salinity Research Institute, Karnal. He was graduated from Jabalpur Agricultural University. He has completed his master's degree from renowned IIT Kharagpur and his doctorate in geoinformatics from Cranfield University, UK. He has vast experience as expert, as consultant in planning and executing drainage systems effectively in Haryana and several other national projects and river basins of India. So I request Dr. Bundela sir to now start his lecture. Please, sir.
Thank you, madam. Good morning to participants and Gorantiwar sir. The topic of the today's presentation is National Drainage Guideline and Cost Norms for Large-Scale Reclamation of Waterlogged Saline Soil for Restoring Productivity. This topic is quite relevant why we need the national drainage guidelines and cost norm for the country? Because there are issues like there is a no cost norm followed in this country. But there are certain programs like RKBY where we have the sub scheme on reclamation of problem soils, where the allocation of cost is around rupees 60,000 per hectare for the entire country. Then another program like CATWM, where the cost norm for open drainage is 20,000 and subsurface drainage is 50,000. When we look at these figures, basically for the large scale implementation, they are highly inadequate. Then the ICR has taken a good initiative in this regard, particularly Dr. S.K. Chaudhary, DDG NRM. He nominated or assigned this task to CSSRI that the CSSRI should come up national drainage guideline for the entire country for different agroecological regions. So on that basis, these guidelines were developed in 2017 and they are also under revision at this time because there are some issues which has been communicated by the states. So we are incorporating that part. And in this particular presentation, we would like to cover the connection between irrigation and soil salinization. There is a good connection I would show you with the examples. Then we need the drainage and land reclamation because alone drainage cannot complete the entire job of desalinization. So that I would give you the emphasis on other part as well. The third part, basically the sustainability of irrigation projects is a good issue and most of the irrigation project in India are under question because they are underperforming. Then the SSD technology for the both major group of soils, alluvial soils as well as the black soils and their impacts. The need for the national drainage guideline and the cost norm for the entire country. Then we would like to have some overview on institutions, policy and national coverage of the drainage in India, and then the new policy initiative in view of the land degradation neutrality to be achieved in India by 2030, because that's the most emphasis and we have to achieve. And here I am basically emphasizing only on the saline soils component in terms of land degradation neutrality. So when we look at this particularly scene, so the salinization of waterlogging starts with a small patch, but with the time it can swallow or it can engulf the entire field. So at the extreme right, you can see there is a barren soil, no germination at all, and farmers are trying. So that's why this is a progression of the salinization. Then this is the extreme case where I have provided the two examples on the left hand for the alluvial soils, right hand for the black soils. And the first site basically in the Rohtak district of Haryana, the second site on the right in the Sadshal village in Sarol Taluka, Kolhapur district of Maharashtra. And we say the both scenario, they are the man-made scenario, man-made wet desert, because these are made by the human failure or anthropogenic factors. Like we have the desert in the Rajasthan, but they were made by the war. So these wet desert, we need to prevent, we need to manage, we need to reclaim them so that the farmers affected by the salinization, they can have the livelihood security in the long run. And this is the country scenario when we look at. So the soil salinization is increasing at the rapid rate. So at 2010, it was 6.73. In 2025, it would be 11.20. And particularly here, when we look at, and in 2025, it will be around 20 million hectares. But when we divide this scenario into two contexts, saline and sodic soil, saline soils are increasing rapidly at the rate of 25 to 30%, and sodic soil is declining at the around 25%. So here when we look at particularly 3.77, and this is not increasing that much. So this is basically increasing at a some rate, but when you look at the saline soil, 2.96 going straight way to 8.46. So that means the major failure is happening in the saline soil or salinization component. So we need to have a more research in this aspect, more clear guidelines, and then we should have a better policy. And moreover, in the recently under land degradation neutrality aspect, India has committed to achieve the neutrality by 2030. So it's a huge task. And now they have allocated around 26 million hectare, in which 8 million hectare area is allocated to the agriculture. And when we come to the saline soil or the salt affected soil, it would come around 3 million hectare. So major would be the saline soil. So that's why we need a national drainage guidelines, we need institutions, we need policy. So what was the problem behind of this scenario? So when we look at the irrigation development paradigm, it looks quite rosy, but it was not unblemished, because the basic misconception was that more irrigation, more yield. So this was the basic misconception. But it resulted, when the more irrigation, it resulted into the more yield. But it was failure on the part of water management front. So because of that, the more salinization is happening. And it was not realized, if you look at here this part, it was not realized at that time. Mega quantities of water in irrigation scheme also introduced mega quantities of salts into irrigated farms. That would change entire hydrology and salt in water balance. For example, I have studied the Western Yamuna Canal command in Haryana. So the per annum salt inflow to the system is around 16.26 lakh tons per annum, which is quite huge salt, particularly coming into the canal schemes. And these salts needs to be flushed out to the drainage, or some level need to be put down below the root zone soils, so that the sustainability aspect of irrigated agriculture or irrigation project can be maintained. That's the reason the irrigated lands start losing the yield gains, because when the farmers got the irrigation as well as the other inputs during the green revolution, they were quite happy with the change they have seen in terms of the yield gain as well as the farm income. And then they have improved their lifestyle as well in the northwestern India, particularly I have seen. But that development was not sustainable, and these land start losing the yield gains in the longer run. The farmers start worrying them. So the factors which are responsible for the soil salinizations, like the average quantum of salt applied to irrigated farms, varies from 1 ton to 2.2 tons per hectare based on the canal, groundwater, or conjunctive use source. So if there is a single source like canal, single source groundwater, then certainly the different combination and the quantum of salts come within this particular range. The second issue basically was the rise of the water table, and that particularly in the saline and saline sodic groundwater zone, was alarming due to the canal seepage and leakage and poor on-farm water management. These all issues compounded by the inadequate drainage, provision in the project, and then increased congestion due to rapid growth of infrastructure project, because projects like railway, road, and other development projects, they hardly bother for the natural drainage. So they basically impeded the capacity of the natural drainage. And that's why this problem got aggravated further and further. Lastly, the drainage was a neglected issue. Nobody bothers because it is needed once a while, maybe in a year or two, it may be needed. But under the climate change scenario, it is now a large issue and it's quite visible even during the monsoon every year. So that's why people now thinking, even the government is now start thinking on this issue. These are the some of the salts work out for the irrigated farms. So if we are going alone for the canal water and with 3 cropping systems here, so from cotton wheat to sugarcane, the 1 ton to 3 ton. So this is wherever the full canal supply means for the entire crop demand is met by the canal only. Then the second issue come up with the groundwater only. So this is only with the groundwater. So here the quantum of salt applied is 5 ton to 15 ton. But normally what happens, the canal is not supplying the entire crop demand. So in the most situation, it's basically the conjunctive use. But normally when we see the groundwater is used up to 5 EC of water. But 5 EC of water cannot be used because this comes in the poor category. 3 EC water comes the marginal category, and up to 2 EC, it's a good quality water. So this criteria is for the irrigation. So that's why when this 5 EC water is used for the cotton wheat, it would add. But this scenario is hardly existing. In a few area, few patch extreme scenario, this is visible. But mostly from here to here, these scenarios are prevalent in the canal commands. Like in the upstream, you would find this scenario very well. But if you go to the down tail end, the groundwater component. But in the somewhere between the mid tail and mid reaches, you would find conjunctive use. So that's why there is a huge quantum of salt applies from the head to the tail. And this is basically is aggravating the situation. But what happened, there is one advantage with our agroclimatic region. We have the monsoon rainfall. So this is the monsoon climate. So most of the salt, when there is a normal monsoon, most of the salt, they leach down below the root zone. So that's why they don't have the effect on the cropping. But whenever there is a break in the normal monsoon, so whenever there is a deficient monsoon, and if it is continued for a couple of years, like it happened in Northwest India, since 2000, every third year is a deficient monsoon. So because of that, this salinity problem is further aggravating. Then come to the systems losses. So in the entire canal systems, the water losses is around 54 to 64% due to the seepage, leakage, and poor on-farm water management. And this water, particularly, part of it goes to the groundwater. So that water is basically recoverable in the good quality groundwater zones. So that happens in Northwest, in other part of the country. The tube well drainage basically in form of the irrigation tube wells that has been implemented, and because of like in Canal and in other areas, so it was the waterlogged sodic soils. But when tube well drainage initially with the public tube well and then later on the private tube wells, the entire area with water logging was reclaimed in around 7 to 8 years. So this area was completely reclaimed. So wherever there is a good quality water that has come up shallow, the reclamation is very simple. Just install the irrigation tube wells, extract the water and go for the irrigation. So it does the both purpose. First, basically, it will lower the water table. The second part, the same water will be used for the irrigation. So the both way, it's both beneficial for the lowering and beneficial for the crop. So that way, the large area was reclaimed, and that's why this level of technology is a farmer level technology. So wherever this is the problem, farmer go alone with themselves with their investment. They don't need any government supports. This is the one of the scenario with the canal irrigation projects. So what was the plan in the irrigation project and what is happening? Because this is I am giving for the why salinization is more prevalent. So particularly when we look at the system optimization in this the example of the Western Yamuna Canal command, so the system was designed based on the water productivity. Means we have to produce more with the same unit of the water. But the current scenario is land productivity because here the farmers have a very smaller land, like less than 1 hectare or around 1 hectare. So they say the limiting factor is land, not water for us. So we have to maximize production from the limited land. So that's why they are focusing on the smaller land. So water productivity, that plant component was changed to land productivity. And that happens when we look at the irrigation intensity, it was 52% planned and currently it is 186. And that major contribution comes from the groundwater, that is around 116% is the groundwater contribution. And because of that, this groundwater is of multiple quality, good quality, marginal quality, and some extent poor quality. The farmer is forced to apply because the emphasis is the land productivity. And then what happened that this irrigation project was planned for single season, that means Rabi crop only. But now farmers going for the two crop. It was planned for low water demanding crop. Farmer is not agreeing with that. They are going for the high water demanding crop for the higher productivity. So because of that, the yield was increased quite a lot. It's around 5 times yield, but here this is two crop. It is only one crop. Then what happened? This was the environmental issue. Initially it was anticipated there will be some salinity problem, so curative measures will be taken up. But ultimately what happened? This resulted into the increased salinity and the water logging in a major way. That's why the canal command projects are underperforming as well as there is a issue of the environmental sustainability. Now come to the saline soil, particularly in the canal command. There are two kinds of saline soils in the canal commands. The first category comes the waterlogged, the second category comes non-waterlogged. So these two categories, they have the different prescriptions we have to follow. For the waterlogged saline soils, majority this category, but there are some cases of waterlogged saline sodic soils. So for that category, we need a third level of the prescription, which we say the gypsum one. But normally, soil, we need first drainage, and then we have to follow the salt leaching. Alone drainage is not a complete desalinization. So salt leaching is more important, and salt leaching basically done in two ways. Wherever there is a gravity outlet, it is done automatically. Only we have to apply the enough water for the salt leaching. But in case of pumped outlet, we need to operate the drainage system for an optimal number of the hours. So then we can achieve the optimal salt leaching. And wherever there is a problem of saline sodic soil, particularly sodic component, after leaching, particularly after drainage, then we have to apply the gypsum and then go for the salt leaching. But in case of non-waterlogged saline soil, only the salt leaching component is required. So these are the some of the reasons why drainage is needed. And here this is basically the all the regions is listed by the RISMA of Netherlands, who has worked with the CSSRI under Inol projects. And first three, they are quite important one, and the other is basically aspect of the health and environment aspect. So the first reason to have the drainage is the drainage protect the irrigation investment, which is quite true. Because if we cannot implement the drainage, then certainly the sustainability of the irrigation project is a big issue. So that's why the drainage is important to protect the investment. The second aspect, drainage sustain and increase the yield and rural income, which is quite true. The third one is the drainage protect the resource base for the food production, whatever the arable area, that there should not be decline due to waterlogging and salinity. So that resource base need to be protected. The other like drainage infrastructure serves the rural and urban resident as well as the industry. Drainage protect the human lives and assets against flooding, high groundwater levels. Drainage services improve health conditions, and drainage regulate the water quality except over conditions. Then the CSSRI research component come. The CSSRI basically they have started the research since 1969, but particularly on the drainage, it was started in 1972. At Sampla was the first site, and there in the entire Haryana, the 10 small pilot schemes ranging from 10 to 40 hectares on SSD that were installed, they were monitored and evaluated. And then the CSSRI come up with the SSD guidelines for manual and semi-manual installations in 1984. Then for the large scale implementation with mechanized installation under the Indo-Dutch network project, around 2,400 hectare at 5 sites or 5 agroclimate regions like Haryana, Rajasthan, Gujarat, Andhra Pradesh and Karnataka. They have conducted the study at quite large scale, and based on that they came out with guideline for the mechanized installation for reclamation of the waterlogged soil. And that SSD technology was quite adopted in 10 states. Punjab, Haryana, Rajasthan, Gujarat, MP, Maharashtra, Karnataka, Telangana, Andhra Pradesh and Canal. And this technology has contributed enormous socio-economic benefit and livelihood security to the millions of resource poor farmers living in the salinized lakes. Then what's the current scenario for the saline soil and how much waterlogged saline soil need to be reclaimed in a next 10 years plan? So the basically the 2.95 million hectare land is affected by the twins problem, the waterlogging, soil salinity, and current economic loss due to this around 8 to 10,000 crores for the country, and immediately 1.37 million hectare waterlogged saline soils in the country need to be reclaimed in next 10 years, because that is target based on the existing assessment of 1996, where the 2.95 was the saline soils. But as this increasing, the more area will come up. But if we can achieve the 1.37 million hectare in next 10 years, then I think that would be the good beginning. And then later on we have to make a more better target and larger target to achieve the land degradation neutrality. This is the technology, basically the SSD. This is the, you can see the barren soils here, completely barren with the waterlogging and salinity. And then these are the, this is for the alluvial soils, and this is for the black soil, black cotton soil. And these are the heavy machinery used, because what happened in SSD installation, basically 3 to 4 operation needs to be done in one go, because these are the waterlogged saline soils. So what happened, when the trench is cut by the machines, then if the pipe is not laid and grade is not provided to the pipe, then the side of the trench they collapse at the same time. So that's why the heavy machines is needed, and all the 4 operations, they need to be done simultaneously, like digging, laying pipe, providing grade, and backfill. So these are the components need to be done at the same time. But there is an advantage with the black cotton soils particularly, because black cotton soils are quite stable soil even with the water logging. The site don't collapse. So in that one particularly they are using this machine. Then later on there is an improvement. They can go with the hydraulic excavator of around 100 to 120 HP. That is working quite well. So far in the country, 71,334 hectare area in 10 states have been reclaimed. So this is the process flow chart for designing the SSD systems. So how we can design and quickly do the modification with the drainage system. So drainage system is always start with the outlet. So here this is the flow chart. So this is the basically information is required, like climate, topography, soils, crop, water table, and salinity. Then we are assessing whether the drainage is needed, particularly the subsurface drainage is needed or not. If based on the condition of the site survey, if feasibility reports say the drainage is needed, then we are straightway going to confirm the outlet type, whether we would have a gravity outlet or pumped outlet. It is based on the topography, but most of the cases we would have a pumped outlet. But in some of the cases of like a lift irrigation command, we could have a gravity outlet. So once the outlet type is decided, then straightway we can go for the drainage coefficient, drain depth, and the spacing. And once these parameters decided, then we straightway goes to the choose the system layouts, maybe the singular, maybe the composite, and then the parallel or grid pattern or herringbone based on the topography of that area. And once this is decided, then we determine the pipe size and the grade. So this is based on the hydraulics of the system. And once the pipe and size is decided, and then the filter is required. This is basically, sometimes we say filter, sometimes we say the envelope. But most of the cases, we are providing the filter. Because what happened? In black cotton soils, where the filter is not recommended, but there the SSD is installed at the shallow depth, and sometimes cracks in the black cotton soils are quite deep. Sometimes they can go to the pipe level. So there is a possibility there may be debris from the surface directly go into the pipe level. That's lead to some level of choking. So for the safety aspect, because system is designed for 25 years, so that's why the filter is recommended for the black cotton soils as well. And this is the criteria for the SSD. Water table should be less than 2 meter. EC should be greater than 8 decisiemens per meter, and pH it should be less than 8.2, ESP less than 15. But this is criteria absolutely applicable to saline soil only. In case of saline sodic soils, these parameters both goes up. So this is the basically the drainage coefficient, this drainage parameters, and here the drainage coefficient, it is based on the climatic regions, arid, semi-arid, subhumid, and this is the range basically. For the arid 1 to 2 millimeter per day, semi-arid 1 to 3, and subhumid 2 to 5. But here for the most of the country, particularly the arid and semi-arid, we are following 1.5 millimeter per day. And then for the drain depth based on the outlet. Once in the flow diagram, once we decided whether it's a gravity outlet or pumped outlet. So in case of gravity outlet, we are going normally from the 0.9 meter to 1.4 meter, because based on the length basically. So, but it should be less than 1.5 meter, and for the pump 1.2, 1.8 meter. And spacing for the different textures, so light textures around 100 to 150 meters. But here normally we would follow 100, 110. We are not going more than that. For medium textured, normally it is range is given 50 to 100 meter, but we are following 60, 67 or 75, but not more than that. For heavy textured soil, 20, 30, not more than. But recently the farmer is more willing to have a narrow spacing. So they are going for the 15. But sometimes 15 is good for the rapid reclamation, but later on that will cause the problem of over drainage. So that's why wherever the 20 meter or 15 meter, we are recommending only with the control drainage. So next one is basically the design equation which are using the transient state global term equation. But for the simplicity, we use the Hoogout equation. Layout, already I said the singular composite, pattern, parallel grid or hiding board. And these pipe size basically for the lateral pipe, 80 mm pipe, we are recommending with grade of 0.1%. For the collector size, 90 mm to 294 mm collectors, this is. And for the filters basically, wherever there is a more than 40% clay content, the filter is not recommended. But as I suggested or already told, for safety of the drainage system, because system is installed for the long term, which is 25 years, for safety aspect, we are, because that cost is quite less for the filter, we are recommending for the longevity of the system. This is the comprehensive design criteria followed for the different soils. So this criteria is for the Northwest India, and this is for the Western and Southern India. Drainage coefficient 1.5 mm per day for the both situations, and then drainage spacing 60 or 67. For heavy texture soils, 30, 20, 15, but 30 is now discontinued, because what happened, the farmers, particularly the government agency, is recommending that one, but reclamation is quite slow. To improve the reclamation, the 20-meter spacing is quite good, and the reclamation is quite shorter, and yield enhancement is appreciable. But only thing is that we have to recommend that 20-meter or lower spacing with controlled drainage only. So that's why in Maharashtra, particularly the Kolhapur district, the 15 and 20-meter project, they are being implemented with controlled drainage only. The lateral depth, already said, this is around 1.5 to 2 meter for the northwest India, and it is 1 meter to 1.5 meter for the western and southern India. Collector depth 2.5 to 3 meters, and here 1.6 to 2 meters. That means the entire operation finished with the 2 meter in the black cotton soils. Then lateral size, as I said before, 80 mm for the both, and collector size it is start for the 160, 200, 250, 294. These are the 4 collector sites for the northwest India, and here the basically 90 to 170 mm. And what happened basically in northwest India, most of the irrigation command, at least there is an open drain. So that's why for the disposal of saline effluent from the subsurface drainage, the open drainage is needed. But in Maharashtra, black cotton soils, some of the projects they have the open drain. But lift irrigation projects, particularly in Krishna and Godavari river, they don't have the open drain. And nowadays the land is quite costly. Farmer is not willing to share the land for the open drain. So what they are suggesting, instead implement the pipe open drain, pipe main drain. So that way the system cost is increasing, but this is a quite good solution for that. And size of the drainage block is 30 to 60 meter, and for the black cotton 20 to 40. And these are the slope provided for the both lateral and the slopes. There are couple of drainage solutions like subsurface drainage, because basically we don't say these are complementary to each other, and we should adopt the integrated drainage approach. It's not like the SSD is better than surface drainage, subsurface drainage is better than surface drainage. It's not like they all have a domain, they are complementary to each other. So the first requirement of the irrigation project is the open drain. Then it reclaimed quite large area, but still there are quite large pockets where the water table is shallow in the saline groundwater zone condition, where we need to have a subsurface drainage. And in subsurface drainage, particularly the horizontal one, the deep open drainage is farmer is not willing, because it needs quite a lot of maintenance. So that's why they are preferring the pipe drainage. So the pipe drainage is quite popular in the SSD. Mole and chimney drainage, they have the domain. But like a vertical drainage, sometimes it does the quite job. But in saline groundwater zones, it creates the environmental problem, because we have to draw more than 10 times volume of water in relation to the pipe drainage. So that's why that create. Then the interceptor drainage along the canals, that can be applied. But in interceptor drainage, there are two kinds. One is the engineering application, and there is a wire drainage. But there is a need of R, that is the integrated drainage. For that, we need to have a drainage master plan in which area, because we need to have the complete aspect of the total drainage. So wherever the prevention part is needed, we have to go for the preventive drainage. Wherever like part of prevention, part of curative is needed, we should go for that. Wherever totally reclamative or curative is needed, we should go for that. So this is the saline soil reclamation package, because here only the drainage component is not that much important, but there are other components which play quite good role, because these are the supplementary component. So like first, in case of like wherever there is a abundant land and we need to rehabilitate or reclaim that land. So we need the land clearing, we need land grading, we need field burning, and then come the surface drain cleaning component. So that component is quite important. And then the installation of the subsurface drainage to control water table and salinity, and then salt leaching. Then the selection of the salt tolerant crop and cropping systems. Because in the first year, the entire salt would not be leached out. So we should go for the salt tolerant crops, which can give the quite better yields, and then follow the improved agronomic as well as water management practices. And above all, the capacity building of farmer or farmer drainage societies are more important, because they must know what to follow when. And for maintenance aspect of the systems, they must be trained and their capacity must be built. This is the basically the implementation part of it. Northwest India. So the first, when the entire machinery is in the field, so first thing is start with the installation, setting up the laser system, because the grade provided by the laser to the pipe. So, so the left hand photo that shows the setting up the laser systems. The second middle photo, it shows the installation of the collector drain by the 400 HP drainage trencher. This is the trencher from the Netherlands, and the make is Holland drain. The model is BS4000. And then installation, and this is the installation of the lateral drain pipes. And there are a couple of implementation mode for the subsurface drainage. In some state, the state department is implementing. In some state, there are specialized agency, and in some state, the drainage contractor or industries are implementing. And recently, the NABARD is also coming to the picture, and they want to promote the reclamation of saline soils. But their major emphasis is on NGO component. The old entire drainage project need to be implemented through the NGO and through they say the PFA, the Project Facilitating Agency. So the CSSRI is also working with the NABARD in Rohtak and Jhajjar district through the NGO. But still there are limitations, because that NGO is not quite large, their capacity is quite small. So still we need to involve the drainage contractor. There we can. So that's basically the pilot models which we are trying. So here what was I saying, like in Haryana there is a HOPP, like in Rajasthan it was Rajat, then in Punjab, the Punjab Irrigation Department, and then come to the Maharashtra, there is a small scale irrigations that department is implementing, and the Soil and Water Conservation Department. In Karnataka, there are 3 agencies involved, like Agriculture, CADA, Waterside. So that's why the pace of reclamation is quite high in Karnataka. What I would said before, the SSD is a highly technical and skilled job. So it's not a very simple, it need a quite lot training to the implementing agency, to the funding agency, and to the farmers as well. Otherwise, they would not know, because the machine is doing the entire operations. So sometimes it's quite difficult to tell them why we need a larger machine for the implementation. If you look at the fleet of these machines, is quite large fleet, particularly in the Haryana. So the project size is normally here 500 to 1000 hectares, which cost around 5 to 9 crores. And if these are the machines required for the implementation, like drainage trencher, it's quite 400 HP machines, then hydraulic chain type excavator to install the manholes and other things. Then we need the bulldozer to clear the path of trench line, because the trencher need a smooth surface so that it can provide a precision grade to the pipe. If there is a bund, there will be jump. So we normally we demolish all the bunds during the installation. So the trencher, the bulldozer is followed by the trencher, and then the bulldozer does the backfilling job as well. Backhoe loader JCB machine is needed to bring the pipe and other stuff to the site, like we have the RCC heavy pipes. So we have to transport them from the road to the site and other materials. And then we need a quite a number of dewatering pumps because it's a shallow water table. So we need to run the pump at least 72 hours before so that water table can go down and we can install the sump valve, RCC sump valve quite smoothly. In shallow conditions, sometimes it's quite difficult to install the sump valve, which is the starting point for the drainage. And then we need the tractor and generator set for the sites. So this, but in case of Maharashtra, we don't need this much machineries because their soils are quite stable. The site doesn't collapse, so we can do the operation with a gap. So that's why the trencher is needed, and then the hydraulic excavator is needed because the bulldozer is not needed. This will do the backfilling job as, and dewatering pump is sometime needed because wherever there is a severe waterlogging, then the pump is needed, but they are not needed. And then the tractor and generator set is needed. So the half number of machines are needed for the black cotton soils. So these are the SSD projects in the Vertisols, particularly in Maharashtra, Karnataka, Gujarat. And here the farmers are growing the sugarcane crop, which is quite remunerative and cash crop. So here the farmers are paying themselves for the cost of SSD, for reclamation, realizing the benefit and impact of the technology on the crop yield and farm income. And this technology in Maharashtra or these states are implemented in the PPP mode or turnkey basis for improving the reclamation phase. This is the one of the project implemented by REX through CSSRI in Gujarat at Moland in Surat districts. This the area was 45 hectares, and there the beneficiary farmers were just 23, and their sugarcane yield increased around 100 to 200%, quite significant. And similarly, the income increased around 140%. That means this technology is quite beneficial, and moreover the return on SSD is quite good. So that's why in Gujarat as well, farmers are willing to pay the cost for the entire system. But they, for the larger scale, because the some farmer they have the capacity, they're coming forward, but there are marginal farmer as well. They don't have that much capacity. So what they are suggesting, they can pay at around 50% of the system for the 50% government should provide. As I told before, because in black cotton soils, the earlier recommended spacing was 30 meters. So in that one, the reclamation was not very rapid. But in 3 years, when we look at the 3-year results, the reclamation was quite good. But what happened, the farmer response was not quite good. So because they want the early gains, so that's why the CSSRI reworked out the design parameter and recommended the 20 meters spacing. but farmer is still willing to go for 15 meter. So there are both cases there, 20 meter and 15 meter, but this spacing was recommended with the controlled drainage as per the national drainage guidelines, so that there will be at least minimum environmental pollution at the downstream. And recently, I think 2 years before, and Srisal is coming with Madam your this course, and in that area, the 9 farmer society funded controlled SSD project with 20 meters spacing, they have been implemented, and that is in 2,400 hectare, and entire project is basically funded by the farmers themselves through the cooperative society. So this is the new way basically. Earlier we were using the heavy machinery like a trencher, but recently the JCB hydraulic excavator that has been deployed for the installation of the subsurface drainage. So this fleet you can see of the machinery which are installing the subsurface drainage. So this is the pipe laying, this is the manhole. These are the project 9 control drainage project, and Sri Sal is coming from the Sri Gurudutt sugar film factory. He would highlight all these issues basically. So quite a good improvement in this part. So what was earlier scenario, like we have the uncontrolled drainage, or we say the conventional drainage. In conventional drainage, particularly in the black cotton soils, there is gravity outlet. So the outlet is running throughout the year wherever water table is higher than the lateral pipe. So that was causing the environmental pollution issues. But at 30 meter spacing, the environmental pollution was not significant. But there was a loss of irrigation water, loss of nutrients some extent. But when this system was implemented with 20 meter spacing, there is quite a lot irrigation water loss and the nutrient loss. So that's why the control drainage was implemented, and here the control drainage you can see better way. This is the control bar fixed at every collectors. So this valve is operated by the farmer as per their requirement. Whenever they are applying irrigation, they shut down it, and whenever they are not applying irrigation or other input, they are opening it. So based on that, they are going to save around 30% water and around 15 to 20% fertilizer they are going to save. But this system is quite good in the terms of environmental issue. And in this one particularly, when we look at, it was from April to November 2018. The EC and SAR of the drainage water was decreased from 28 to 4.8. Quite a lot change in the salt load in the water. And similarly, it happens for the EC of the soil. But the pH was increased because this soil is not saline soil. Absolutely, this is the saline sodic soils. And in this project, the open drainage was not available. So the SDP double wall corrugated pipe drain was implemented, where it has the diameter of 135 mm to 500, quite large diameter pipes. So some of the picture I will show you a little later. The cane yield increased from 33.7 to 51.4 tons to 78.5 to 97 tons in the first year itself. So quite a Good response was realized by the farmers, and then since the CSSRI is facilitating in the National Drainage Guideline, so we are also conducting the meeting with the Commissioner Agriculture at Pune, Chief Engineer Small Scale Irrigation, and Director DIRD, where we are basically discussing and sorting out the issue why large scale reclamation is not happening in Maharashtra. So some of the photograph here, this is the 500 mm, the pipe main drain with the farmers, and this is the basically cooperative society at the Kolhapur, particularly Shirol Taluka, and this is the chairman of Sri Datta Sugar Factory, Datta Sahab. This is the impact. So the SSD technology has a quite good impact, appreciable impact, where the crop intensity is increased by 40 to 50%, crop yield by 50 to 110%, different crops like rice for 30 to 110%, wheat 20 to 120. Similarly for the sugarcane, 100 to 200%, farm income by 200 to 300%. BC ratio is quite good, 1.5 to 3.2. Cost recovery 2 to 3 year. Annual rate of income 20 to 58%. And besides that, it generates 128 man days of employment per hectare annually. That's quite good. So there is a quite a lot employment generated by these projects. And in terms of the soil salinity reduction, so pre-project salinity was around 10 to 40 T. It was reduced to 2 to 5 decibel per meter in 2 to 3 year period. So it's making quite significant impact in terms of salinity reduction, in terms of yield improvement, in terms of income improvement, as well as lowering the water table in salinity. Then now we are coming to the national drainage guidelines. What component the cost norm this has been included here. So because what happened, our emphasis was whichever agency is implementing the drainage project, it should have the totality for the implementation. So any component should not be missed out wherever that may be the constraint in implementation. So the 8 component basically they were implemented, and the other component is also listed in the rider as well because they are not applicable at every project. So in some special cases that rider is also there, like a field survey and investigation, planning and design. So that include the preparation of the DPR basically, and ultimately up to the tendering process, because here we were emphasizing not only the state government agency, the other drainage industry, drainage contractor, they must come, because for the larger goal, we should invite the every sector, even the private sector efficiency, we can harness through these guidelines to achieve better reclamation pace. So that's why based on the CPWD norms, we have provided based on the 2070 2,500 rupees per hectare. That amount is provided here. Then the cost of drainage material and its cost, installation using particularly the larger scale. That means the fully mechanized mode was considered here. And then the supervision of material installation quality. So that cost is included 4,000 per hectare. Operation and maintenance. In case of pumped outlet, the 500 per hectare. But in case of gravity, they can utilize same money for the outlet protection as well. The contingency is 5% of the project cost. Farmer awareness training. 750 per hectare. That is the 1% of the project cost. Monitoring and evaluation, but it is not needed for all the project, but some of the project is needed to assess their impact in the terms of the crop yield and farm income as well as the technical aspects. So these are the drainage material used, like a lateral pipe. They are the PVC flexible corrugated perforated single wall corrugated pipe. Particularly here, the mostly the 80 pipe, diameter pipe is used for the lateral. With conforming, these are the IS standards. Then collector and main drain, corrugated PVC, and SDP for the main drain. This is the diameter, synthetic filters and envelope. So two type of filters is used, one for the lateral, another for the collector. So here the non-woven polypropylene fabric is used for this one, and for the collector, woven. The woven nylon socks is basically used for the northwest India, but not used in the black bottom soils. Structures and pump sets like manhole, junction box, sump well, outlet structure, pump houses, and the diesel pump set. So these are the material. This is the lateral pipes. This is the collector pipe. This is the SDP pipe for the main drain. And then we work out the quantity required for the installation into a drainage block. So whenever the spacing changes from 20 meters to the 100 meter, because this is the more optimal range for the entire country. So for the 20 meter, basically the lateral pipe is needed 20 kilometer for a 50 hectare block. So, and for 30 meter, 13,600, and similarly for the Haryana, like here we use the 6 kilometer lateral pipe length for a 50 hectare block. And then the collector pipe for the every drainage block. So for the black cotton soil 400, and then for 200 meter 330 meter and 250 this one. So this way, this is the collector length of 1 kilometers and 20 kilometer for the lateral, and then the wrapping of the pipe for all this. So that way the entire quantum of material and how much will be the manholes per block, that has been 3. Like a sump well, this is like we have written here, the item 6, 7, 8 and 11 is not needed for the gravity outlet for the black cotton soil. So that way that component is not considered in computing the cost, but here it is listed. So similarly, in that way, so like when we say the lateral length per hectare, it comes 120 meter to 400 meter for the entire country. But that is the range basically for collector 20 meter, but it may change based on the proximity of the open drain. So these are the material and their unit cost during the 2017. So PVC corrugated and perforated pipe, these are the pipe for lateral, and this is for the collector. We consider the unit cost is given here. So it varies from 58 rupees per meter to 870 per meter. Nylon soaps, the cost is around 45 per meter. And then for non-woven, it is come 47 rupees. And RCC pipe, the sump well, it is costing around 33,000, and manhole 14,000, and diesel pump 47,600. And these are the government approved rate basically taken from the Haryana government. So once we work out the entire cost for the for a different combination, like pumped outlet, gravity outlet, then alluvial soil or heavy soils. So these are the basically the 4 curves you could see on this particular graph. So this is the first one, is the gravity outlet for the northwest India. But in northwest India, there are hardly gravity outlets. There are hardly. Mostly they are the pump out. So this particularly blue curve is more applicable in northwest India, which cost around 85,500 to 61,000, based on the spacing. And then here when we look at the black cotton soils, particularly in black cotton soils, the gravity outlet is more prevalent. But there are some pumped outlet like in Andhra Pradesh, there are Karnataka, there are. So that, but in case of black cotton soil, as a general scenario, the normally this violet line is more applicable. So this is started with 20 meter, but in this one, but normally that included the 2,000 rupees for monitoring and evaluation, because the every project is not monitored and evaluated. So that's why this cost comes 48,500 for 20 meters. This is the cost breakup for the different spacing, like for the heavy texture soil. Here I am giving the 30-meter one. This is for 67 meter. So what would like to say that here when we look at the material cost, it comes around 54%. These are the material, three material: pipes and fittings, filters and structures. So that cost 54%. Then installation cost is 33%. So that both, if you include, it comes 87%, that cost. Similarly here that's also come equally, 29%, 11% and 9.8%. So here the cost would be little lesser than the black cotton soils of the material, because here the less material is used. So that way we are giving the structure, how much component has a share in the entire cost. So this was the drainage guideline and cost for the SSD, was published in 2017, and then this guideline was submitted to the ICR NRM division. From there it was examined and then submitted to the by DG ICR to the Secretary Agriculture. Then later on, the Secretary ICR as well as Secretary Agriculture, they communicated this guideline to the Chief Secretary, Agriculture Production Commissioner, Principal Secretary, Agriculture, to the 12 states for inclusion to the RKBY and other programs, because they suggested this guideline is quite comprehensive. So these are the state: Maharashtra, Punjab, Haryana, Rajasthan, MP, UP, Gujarat, Maharashtra, Karnataka, Andhra Pradesh, Telangana, TN, Kerala. These 12 states, and this is the sample copy of the letter communicated to the state of Karnataka. Similarly, we have the couple of letters here. The DG ICAR has also written to 12 concerned states, and total they have forwarded 35 letters to make this program as a state program to the state governments. And here this is the cost table of the subsurface drainage. So the cost of SSD with pumped outlet for alluvial soils, which is applicable to northwest India, ranges from 72,000 to 77,000. With adjoining open drains, because that is a condition for the most of the project, the open drains should be to the adjoining of the project area. But later on that scenario was not happening. Then there was provision was made to the extension of the collector with the cost of 15,000 per hectare. Because if that scenario is not happening, then we can take up the project with this rider. This cost may be additionally provided to the projects. Then cost of the SSD system with gravity outlet for black soils, particularly in the Gujarat, Maharashtra, Karnataka, Andhra Pradesh, Telangana, these 5 states. It's come for 30 meter, 1,09,500 and 1,48,500 for the 20 meters with adjoining open drain availability. But in some of the lift irrigation canal commands, the open drain was hardly constructed. So that's why the SDP pipe drain was adopted. And additional cost was coming around 65,000 to 72,000 per hectare because the pipe size is quite large, starting with 200 to 500 millimeters. And this is the basically the scenario like a pumped outlet, medium light texture. This is the Haryana case. This is the Maharashtra black cotton soils in many states. So gravity outlet 148, as I said before. So this is this. These are the some of the rider what was included in this national drainage guidelines, what was not included. So for that extra provisioning. Like the above SSD cost does not include tree removal, cleaning and deepening cost of the drain, approach road, land development, maintenance cost, farmer share, and the pumping cost for the second year onward. This includes the collector length of 25 meter per hectare, assuming the surface drain in vicinity. If the additional length is needed, that can be provided, that we have provided that detail as well. And these guidelines, particularly the light and medium textured soils, are applicable to Haryana, Punjab, Delhi, and part of Rajasthan, MP, and UP. For heavy soils, these are applicable to Maharashtra, part of Karnataka, Gujarat, Andhra Pradesh, Telangana, Rajasthan, MP, and Tamil Nadu. This much area so far we have covered using the with the existing institution and existing policies. So the major contributor here is the Karnataka, and then Rajasthan, Haryana, Maharashtra is only 6,250, Punjab, and that way the only just 5% of the affected area has been reclaimed in the last 25 years. So that progress is not quite significant. As we see the increase of the soil salinization and waterlogging at the countries. So the problem was basically with the policy. So we have highlighted some of these problems like the implementation of the SSD technology or drainage technology is a highly skillful job and mechanized work. So it cannot be implemented by the every department. They need to have a capacity. They need to have a trained manpower, and so that way, like the department can take up the like they say, okay, we will take up the SSD project, but later on they realize they cannot implement it. Then the second problem was the current cost norm. This cost particularly given for the open drain and subsurface drain are highly inadequate. Like wherever the cost is coming, minimum 110,000, and where it is just providing 60,000, 50% of the less than 50% of the cost, how the department would take up the program? So that was not possible. So that's why the many departments they came forward and they resisted. They said, no, there is no point of implementing because this is infeasible. And because of this, they have the country scale, the progress is quite insignificant. I would say particularly the 5% in 25 years, nothing basically. And if you look at the sodic soil reclamation, where we have reclaimed around 42% area in last 35 years. So that made a significant impact. And for this, there are many issues which we need to look into in view of the land degradation neutrality and other policy aspects. Like existing, no integrated and centralized organization for drainage in this country. In some state, the SSD is implemented by agriculture, small scale, waterside, CADA, and surface drainage only exclusively by. For surface drainage, there is an agency, but for subsurface, there is no agency at the country scale. So, because of that, there is a many issues with this SSD, so that need to be integrated and need to be institutionalized at the state of national scale. So, where we started from the first slide, and here we will be providing the complete solution as well. Like here, if we follow the poor water management, it will result into this scenario. So this is the technology component where we should implement the drainage and the leaching. Then in long run, we could achieve the sustainable productivity in the canal commands. So this way, so this is the solution, and this way we should go for. So this is the pathway basically. What would be the pathway in the coming year, next to 10 years, in view of the National Agricultural Drainage Guideline, existing policy, institution, and funding need to be revisited and improved to address the issue of slow pace of implementation of drainage technology. And then there is a need to have a drainage policy paper at national, at state level, emphasizing the time-bound action to reclaim the waterlogged salt-affected lands. And further to it, there is a need to have the state command or basin-wise master drainage plan to be prepared under the National Water Policy 2012. And then the exclusive policy, because what happened under the RKVY, the subsurface drainage is clubbed with sodic soil, acidic soils, and other problematic soils. So what happened, whatever fund comes under that sub-scheme is utilized by the easier programs, where they have to distribute lines, gypsum, and other component, and those departments are quite comfortable. But SSD being a complete technical job, the department is not able to deliver. So that's why if there is an exclusive program, then some easier program cannot eat its money and taking the advantage of the SSD. So it needs an exclusive policy, exclusive funding, as well as dedicated institution for reclaiming the waterlogged saline soil with emphasis on project outsourcing. Government agency cannot achieve these bigger targets. So we need to harvest the efficiency of the private sectors. So they can play a bigger role in the implementation. The government agency can play a major role in providing the support to the private agency. So it's like a win-win for both, because with the government department, there is an issue nowadays. Most of the department, they don't have adequate manpower, adequate or old machinery, I would say. So like in Haryana, earlier they used to reclaim around 15 to 1600 hectares per annum, but recently hardly 300. Because their machines are so old, there are less people, mostly retired. So that's why in those scenarios, like giving the entire task to the state department may not be feasible to achieve in long run. So that's why we need to invite the private institutions, private industries to harness their efficiency to achieve this larger goal of reclamation of waterlogged saline soils. So that's all, madam. Thank you very much
Thank
for
you, sir.
giving the opportunity. Thank you.
Thank you very much.
Thank you, sir. Now all the participants are requested to please drop your question in the chat box. Sir, there are some questions from the participants.
Yeah, welcome. No problem.
Yes, sir. Yes, sir. First one is what are the chemicals which we are collecting through drainage system, and can we use it somewhere?
Uh, the chemicals or salt comes with the effluent. Normally they are sodium sulfate and sodium chloride. Most of the cases. But it's very difficult to precipitate them because that EC is not quite high. So if that water could be used for some of the application, that's most welcome. But in terms of crystallizing that salt is quite difficult. Thank you.
Darvi, do you want to take some more questions or? Hello, Darvi? Dr.
Hello.
Darvi?
Hello.
Do you want to
Sir,
take
next
some
question.
more questions?
Yes, ma'am. Yes, ma'am. There are more questions in the chat box. Sir, next question is, can we adjust the salinity by some chemical treatment instead of drainage?
I think this is quite a good question, but there is a quite large misconception as well. See what happened, the saline soil have a neutral salts. So neutral salt, the chemically you cannot change their chemistry. So ultimately you have to remove these salts. Like in case of sodic soils, there is certainly the ions play a bigger role. So there you can apply some chemicals and that can be resolve the problem. But in case of salinity, so far there is a no solution to add with the chemicals. Only you have to flush out these neutral salt out of the systems, out of the affected area, so that the normal root environment can prevail or better yield can be realized.
Okay. Thank you, sir. Sir, next question is subsurface drainage is suitable for contour or hill farming?
In hill farming, the subsurface drainage is practiced, particularly wherever there is a localized waterlogging. Like in a tea plantation, I have observed that part. In tea plantation, because it is done on the rolling land, so the tea is sensitive to the waterlogging. So there they are providing deep open drain, from which system they remove the entire excess runoff from the area to the downward area. So that way that's possible. But if the hills provide the natural drainage system, then certainly we can use the natural drainage. Then the artificial drainage is not needed.
Thank you, sir. Next question is, what should be the maximum length of lateral for 80 diameter perforated pipe?
Yeah, I think that's a quite good question. But see, in conventional drainage system, we were going around 450 to 500 meter maximum lateral. But recently we implemented the control drainage system, and there the hardly the length goes to 150 meters. That's all. Thank you.
Okay. Sir, next question is, which is most effective, surface drainage or subsurface drainage, and why?
Okay. I think this is a quite good question. See what happened. Normally the first prescription for anything, for any waterlogging or salinity come with the surface drain. So these are the basically complementary. We cannot say these are the substitutional technology, these are the complementary. So first we need to provide the surface drain and then the subsurface. Because I have seen this is a misconception. Basically, we think like these are the substitutional technology. Wherever we have the subsurface problem, we cannot address by surface drain. And wherever there is a subsurface problem, we cannot resolve by the subsurface. Because what happens if you convert like if you have a fever, so for example, suppose if you have a fever, just take a medicine. Why we want to convert into the pneumonia and then admit into a bigger hospital and then pay a bigger money? So that's why first we recommend for any command, wherever this problem is there, they should have a surface drain, and then the leftover area with subsurface waterlogging or with salinity, we should go for subsurface. So these are the complementary technology, not substitutional technology. Thank you.
Thank you, sir. So the next question is, can APSA80 chemical is suitable for waterlogged areas in crop field?
Which chemical? Let me know.
APSA80.
And can you elaborate? This is chemical. I heard it, but not exactly. I'm getting the chemical component.
Okay. Sir, Dr. Patil, Anil Patil, sir, please elaborate your question in chat box. Sir, next question is, shouldn't leaching of salt rather decrease pH instead of increasing pH?
I think that's a good question, because in complex scene, what happened? Normally we say saline soil, sodic soil, they are the distinct. And normally we have the technology component for both soils are different. But in nature, there is complex problem where there is a salinity, sodicity, waterlogging coming together. In that case, what happened when you leach out? Because what happened, we have to implement the leaching of soluble salts. So when soluble salt leach out through the drainage from that area, certainly the sodicity become the dominant. So that's why that's resulted into the increase into the pH. And for that we have provided the recommendation of gypsum. To provide the gypsum, then the problem will be fixed to the some level.
Thank you, sir. The next question is from Venkatesh, IRI New Delhi. Nowadays, in cricket ground, they are using suction process to remove the water.
Yes.
So, is it suitable for agriculture drainage suction process?
Yes, we are working on that part. That's we say the sports drainage nowadays. So this is the same component of the agriculture subsurface drainage, but here the only part is that we have to remove the water very quickly. So here the pumping requirement is quite high because the time given is quite small. So that is being done in now India, but earlier that used to be done in Europe quite well.
Thank you, sir. Sir, next question is, why the lateral length is increasing with the change of texture from heavy to light soil?
Lateral length is changing.
Increasing. What is the reason behind that?
Because
With the change of
yes, because the hydraulic conductivity is quite less in the vertical, so this black cotton soils. So the quantum of inflow is quite less, so that the pipe size can handle the larger area. So in that way, the larger will be the length in the heavy soils.
Sir, previous question was ASPA80. Sir, Dr. Patil sir elaborated the question. Sir, ASPA80 is the water molecules breaking chemical marketed by Amway company, MISTI for absorption.
I think that part we need to study, because it's still not clear. So far, I have seen the world literature of saline soils. Nowhere I have find any chemical which can change the chemistry of neutral salts and neutralize the salt in that way. I think we need to study or to have a more detail on that. This time it's
Thank you
difficult.
very much. Thank you very much, sir.
Thank you.
Now most of the questions are got clear. So I.
Or if you have any further question, you can email to me. I'm willing to answer whatever question.
Yeah, Dr. Darvi, are you there? I think there is an electricity problem in our cast office. So probably he is not online now. So I thank you. Thank you, Dr. Bundela, sir, for sharing your hard-earned experience and knowledge in respect of agricultural drainage. I'm very sure that this is really a useful session for all the participants who have joined this training program. And now it is a great comfort to know that through the guidelines that are established by CSSRI, we have not only the design norms, but also cost norms that are available, which was really a hurdle for implementing the drainage systems throughout the country. And these norms and guidelines will be very, very useful to various governments, as well as the funding agencies, various NGOs, and also the farmers groups who want to implement drainage system in their areas. So this is really very comfortable to know that the guidelines and norms have reached to different government departments, and those will be implemented soon. So I'm really grateful to you, sir, for accepting our invitation and also providing this hard and synthesized knowledge to our participants. And we expect the same kind cooperation in future. And I wish you all the best for for imparting these guidelines throughout the country, and also for your policy brief. Thank you very much, sir.
Thank you, madam, for giving me the opportunity. Thank you.
Dr. Darvi, are you there?
Yes, ma'am.
Yes.
Sorry for interruption due to the network problem. Now I request all the participants, please be there. For afternoon session, we will share the link 20 minutes before. And the quiz will be provided at the evening for both the sessions together. So I'm very much thankful to Dr. Bundela, sir, for such a nice presentation. And with the permission of the organizer, I